Hey everybody, for today's lesson you're going to need this Post 4.0 bell ringer, which is going to be needed to be handed out to you if it hasn't been handed out already. You're going to need this 4.1 notes handout, and you're also going to need this 4.1 more on slope discovery handout, as well as the 4.1 homework for after the video is all over. But let's start with the bell ringer. Once that has been handed out, take 4 or 5 minutes, all right, and give this a try. So I'm going to need you to give like a hard pause on the video, whether it's you or the substitute. Pause the video, and then after 4 or 5 minutes of giving this a go, unpause. Alright, I'm going to continue on and assume you just unpaused. And so here's the quick rundown of the answers. GCF for 1, 2, and 3. The greatest common factor of 12 and 8 is 4. So that's the largest factor that 12 and 8 have in common. And then as far as the x's and the y's, remember, you're just going with the smaller of the two exponents. So as far as like x and x to the fourth, you know, this has an exponent of 1, you're going with just x, or x to the first, and then the GCF of y to the third and y to the second is y to the second. Just going with the smaller of the two exponents for each variable. Number 2, the greatest common factor ends up being 6x squared y to the third. When you're looking at 6 and 18, remember 6 is a factor of 6. So we got a 6, and then x to the second, x to the fourth, go with the smaller one, y to the third, and y to the third. It's a tie. So you just go with the power of 3 in your overall greatest common factor. Number 3, the GCF ends up being just x, or x to the first. Because with like 4 and 7, the greatest common factor is really just 1, which normally you don't even think of it that way, but yeah, technically the greatest common factor is 1. And then as far as like x and x to the second, again, you go with the smaller exponent, and then it's like you have no y at all and y to the second. So what's smaller between that? It's no y at all, or technically y to the 0 power. And then for 4, 5, and 6, it's LCM. That's least common multiple. So as far as 10 and 4, the least common multiple is 20. And then when you compare x to the first and x to the third, now you're looking for the least common multiple. So now you're going to go with the larger of the exponents for each variable. So x to the third and then y to the fourth. Number 5, the answer ends up being 30 x to the fourth, y to the second. So 6 and 5, the LCM is 30, least common multiple, and x to the second and x to the fourth, and then y to the second, it's a tie, y to the second and y to the second, so you just go with y to the second. Number 6, the LCM ends up being 10, you know, just like one of the ones above there. Don't forget, 10 is a multiple of 10. So between 5 and 10, the LCM is 10. And then with the x's, we go with x squared. With the y's, we go with y to the third, the larger one. And then we have z to the first. And then over here, no z at all. So in the LCM, we go with the larger one, z to the first. Okay? So what you're going to want to do now, no need to pause the video, but I'll pause myself here for about 30 seconds, maybe a minute, and get those passed forward. Okay, pass those forward. No need to pause the video. The substitute can collect those, and as I look to move on with this, but again, take another like 30 seconds or so, okay? Hopefully you can have that stuff collected in another like 10 seconds or so, and we can move on with this little activity. You don't have a paper for this, but just kind of watch as we kind of run through this little brain challenge here. So the question now is, which section is the steepest? Take a look. Which line segment, like which section, would you say is the steepest section? And we'll try to run through this. Maybe we'll kind of fast track this. We'll get through this a little quicker than we normally would. But the next step in this little activity is to kind of point out something like this, where it's a little bit easier to, label one of the sections. If it was like, if you had stuff like this, like you could say segment AB or BC or CD. Just with these labels, it makes it a little bit easier to point out which segment you're talking about. So what else? And hopefully you've been thinking a little bit like, well, how would you know which one is the steepest? Like, how could you prove it? You know what I mean? You might already have one picked, like which one you think is the steepest, but how could we verify beyond a shadow of a doubt which one is the steepest? I mean, what could we do? Like, get out a protractor and like literally measure angles? I mean, like what could we possibly do to know for sure, like which one was the steepest? You know what I mean? And again, we're kind of fast tracking this. Like normally we would kind of drag this out and discuss this probably like in length or at length. But basically what we usually come to is this sort of deal, where it's like, well, one of the best ways, maybe the best way to verify which one is the steepest, is to put this up against a grid, okay? Because steepness, or what we're going to call slope in a couple minutes, is a comparison of not just how much it goes up, like as we go from like point C to point D, or from point A to point B, or B to C. It's not just how much we've gone up, it has to be a comparison, like a combination of how much we've gone up, but also gone forward or to the side at the same time. So it looks like going from A to B, we've gone up 3 squares, but also over 2. And then for C to D, I'm sure it's come down to like, is it A to B? Is it C to D? Are they the same? Is this a trick question? But this one's gone up 3 and over 2. And going from C to D has gone up 1, 2, 3, 4 over 3. Okay, so again, the bottom line here is sort of realizing here that it's like a ratio, a comparison. And so if you were thinking segment CD, let's compare that literally. Oh, looks like segment AB is a little bit steeper, at least. So it turns out anyone that was in the AB camp, you were correct. But let's get down to the real business here. Section 4.1. Alright, so get this paper in front of you, and let's do the, the main part of the lesson here. Alright? Finding and interpreting slopes of lines. Alright, so here we go. The first little note here is saying that we are going to be using line graphs that look like the following 4 pictures. So draw this line and then something like this. Probably should reveal these sooner rather than later. That this is essentially an uphill line. This is essentially a downhill line. And then think to yourself a second, like, what do you think kind of line we're going to call this right here? Horizontal is the third different kind of picture of line graph. And then what do you think the last one is? Vertical. Okay? Now, in a way, this is kind of like putting the cart before the horse a little bit, like revealing these 4 pictures right out of the gate, but maybe not so much. So here is the other thing about these pictures. If a line is going uphill, what that's going to basically mean to us is that the slope of the line is going to be some positive number. So an uphill line like this has a positive slope, which is, like I hinted at a few minutes ago, is kind of like the steepness of the line. And then any line that's downhill would have what kind of slope? You guessed it, negative slope. And then here's where we get a little bit more. Again, we're kind of like giving you like this broad summary, like right at the beginning here. Like maybe we could have saved it for the end, but I think either way. So here we go. We get to like some real special cases. Horizontal line. I don't know, maybe if you remember this from your background in middle school or whatever, but what kind of slope does a perfectly horizontal line have? Turns out that it's 0. The slope equals 0. And what kind of slope would a vertical line have? I don't know, maybe you remember this, maybe you've learned this already, but we actually say that a vertical line has no slope at all, or like undefined slope. Okay, like it doesn't exist in a way, so no slope. Hopefully I can remember to kind of circle back to these, like once we've done all of these, we've taken down all these notes. It'd be worth coming back to like especially the horizontal and the whole vertical deal. But here we go. So in general, we could have led with this. Like this could have been the very first note we took. We will explain how steep the slope is by writing the slope as a positive or negative fraction, like I said, or 0, or doesn't exist. But so in general, slope, like I was hinting at earlier, it's got to be a comparison, with how much you go up or down, along with how much you go to the side. You know what I mean? It's got to be like a combo with that, like a ratio, a fraction, like literally a fraction. Because a fraction is a comparison, it's a ratio, and so slope is going to be rise over run. It's very important you get that correct because it's not the other way around. It's rise over run. Like how much you move up or down in the numerator, and then how much you move to the right or left in the denominator. So rise over run. So here's how this works. Find the slopes of these examples just by counting. Okay? Well, if we're going to count our rise and our run, you're going to need to have like a starting point and a finishing point. So, you have to find, like, according to like the grid here, on your graph, you got to find like real nice coordinates, right? So it's really good to have like nice integer coordinates to kind of start your counting and stop your counting. So you got to find like real nice intersection points of the XY plane grid, like here and here. Okay, like you wouldn't start counting here, you wouldn't start counting here. Like you want to have like really nice integer coordinate spots to start and stop counting. So if we count our rise and our run to go from this point to this point, it looks like we are going up 2 and then to the right 1 box. So up 2 boxes or squares, and then to the right 1. All right, so here's one of the big ideas of today. Going up is a positive direction. So up 2 is positive 2, whereas down would be in the negative rise direction. And then then we go to the right for our run. We're going to the right. Now, what do you think is the positive direction when you're doing like right or left? Like is right the positive direction, or do you think left is? Like, I'm sure you can guess that going to the right is the positive direction. So we have like a positive 2 rise and a positive 1 run. When you put all that together for like a nice final slope, positive 2. So positive 2 divided by positive 1 is 2. What happens over here in this next example? So I picked that point to start counting, and this point to stop counting. All right. So again, it's rise over run. So if I'm going from this point to this point, it looks like I'm going down and then to the right. So down 1 square, which is a negative 1 rise, and then to the right 1, 2, 3. And remember, to the right is the positive run direction. So overall we have a negative 1 divided by a positive 3, and with slope we are absolutely going to want to usually, if like almost always, keep it as a fraction, like pretty much always, okay? So don't make this into a decimal, right? Leave it as a reduced fraction, and in this case a negative divided by a positive is overall negative. Again, because remember, downhill lines are supposed to have a negative slope, just like this uphill line had a positive slope. All right? Moving on to the next example. I will pause myself. No need to pause the video, but I'll pause for like 20 seconds and try this one on your own. All right? And I'll keep going in about 20 seconds. All right, so let's, whatever you were doing, pause, and let's make sure we get this right. So number 3, it looks like I picked this point and this point. You should have got a rise, well, of plus 5. 1, 2, 3, 4, 5. Up, and then to the right 3. So overall that's a positive 5/3 slope. All right? Remember, leave it as a fraction. Don't go with a decimal. All right? And then number 4. Okay, let's look at number 4. Again, I'm kind of giving you some help here, with like as a spoiler about like maybe this dot and this dot to count your slope. So again, it's rise over run. So let's start counting here, and then we got to go down and to the right to get to this other point on the line. So down 2, which is the negative direction for rise. So down 2 and then right 2. Going to the right is positive, and then what's negative 2 over positive 2, like reduce 2 or end up equaling? That's right, -1. -1. So that's the final slope for number 4. All right. So that was finding slope through counting. Like if I was showing you the picture of a line, this is one of our objectives today, is to be able to look at a graphed line and tell me the slope by just like counting, a nice point, integer coordinates, to another nice enough point, and just counting the rise and the run. Next, what we're going to be doing is talking about, well, here we go, let's just read this. Instead of counting, there is also a formula we can use to find the slope. This is especially helpful if you cannot graph the 2 points. Yeah, I mean, here's the basic situation. If what you are given is 2 ordered pairs, like if I give you, I don't know, just for, oops, sorry, I hit my $20 microphone. I just smacked in the mouth there, so I don't know if you heard that. But slope, like if I gave you, hey, what's the slope of the line that contains these 2 points, like something like this, like that would be the basic situation. You don't have to write that down, but this is probably the situation we'd be in, right? If you are given coordinates, right, and asked, hey, if there was a line that contained these 2 points, what would its slope be, right? Now, look, I want to be thorough here. I don't want to go too fast, and it's worth kind of mentioning this, right? In theory, especially if you had a nice blank XY plane with nice grid, you know what I mean? In theory, you could plot those 2 points and just count your rise and your run and put them together in the rise over run fraction and come up with your slope, right? Like in theory you could do that. But I mean, I don't know. If you don't have a nice XY plane, if you don't have like nice graph paper, handy, I don't know, maybe that's not the best way, Or I'll do you one better. What if this was like 25, 71 and like -42, 89? You know what I mean? Like what if you had some like really large coordinates or something that just wouldn't be really conducive to actually plotting and then actually counting? So that's why we have this very nice formula. This is a major formula in the world of high school algebra, or just algebra period, okay? A major formula. I mean, if you look on my wall, it's one of my big wall tattoos, right? This formula for slope, and the ingredients of this formula would be coordinates of 2 points, okay? I mean, this formula basically says rise over run, because that's what slope is. I mean, if you look at this and you see like, oh, we're taking like 2 y coordinates from 2 different points and we're subtracting them. If you think about it, oh my gosh, that makes perfect sense. That's how you would pretty much figure out in a formula the rise. And then if you take the two x coordinates from two different points and you subtract them, isn't that exactly what you would probably have in a formula to figure out the run? You know, in other words, this is another way that people say slope is change in y over change in x. You know, again, rise over run. So just a formula for rise over run, but it's a really classic useful formula. And let's do a couple examples seeing this in action, right? So just like I was saying, the directions will say find the slope of the line between the 2 points, or like a line that would contain both of those points. Then plot the 2 points. You know, we're going to go the extra mile here. This is not a normal part 2, you know, but then we're going to plot the 2 points to see if your answer makes sense. All right, so here we go. In example 1, we have 5, -1 and 1, 4. So like I said, in theory, you can, in fact, we're about to after this, but you can plot these and then like count the rise and the run. But we're going to use this formula, okay? And again, what this says is y sub 2 minus y sub 1 up here in the numerator. In other words, your second y coordinate minus the first y coordinate. So I'm going to call that my y1, my first y coordinate, you know. And I'm going to call this, the 4, my y sub 2. All right? Because again, remember, these ordered pairs, they both go x, y, x, y. That's my first y, that's my second y. So what would that make 5? Wouldn't that make 5 my x1? You know, this is my first x and y, and then 1 over here would be my x sub 2, you know. My first x, my first y, my second x, my second y. So once you figure out what you're plugging in and you get you're careful and you get this correct, now again it's a formula. So you just plug that stuff in. So y2 was 4, and then there's a minus. This is really important to understand here and notice. There is a minus built in to the formula. So there's the minus. Now y1 is -1. So yes, I mean, the top here ends up saying 4 minus a -1. On the bottom, x2 was 1, x1 was 5, and so this is what we end up with. And now you just kind of take, run with this. And 4 minus a -1, that ends up being 5. And then 1 minus 5 ends up being -4. So what can we do with 5 over -4? Does that reduce at all? No. So the overall slope is going to be like -5/4. Like the overall slope is going to be negative here. And you're going to see that if you actually plot these points, 5, -1, and 1, 4. So let's see here. There, right here, is 5, -1. And then this point right here is 1, 4. I'm going to take the opportunity right now to say this, to point this out, no pun intended. People can easily mix up plotting XY coordinates and slope. Remember, when you're plotting 1, 4, you're going right for the x coordinate, then up 4. To plot 5, -1, you're going to the right 5 and then down 1. Slope, being rise over run, is kind of the opposite. You do the rise, you do the up or down, then you do the right or left. So again, case in point, to figure out, to verify this slope, right? you could go down 5, then to the right 4, which gets you an overall slope of negative 5/4. But more on that later. Number 2. So same thing. That's x comma y. That's x comma y. So I'm going to call this my x1. I'm going to call this my x2. And then this is, of course, y1 and y2. So then we plug all these numbers into the formula. Remember, there are minus signs built in here. So y2 was negative 3. y1 is 4. So that's what my numerator now says, negative 3 minus 4. And then the bottom is going to say negative 5 minus negative 2. Right? Remember, there's a negative built in, then x1 itself was negative 2. So where does that get me? Negative 3 minus 4 is negative 7. And then negative 5 minus a negative 2. That's like doing negative 5 plus 2. Negative 3. Okay, so what happens with this fraction? Does it reduce at all? Not really, other than, a negative divided by a negative is overall positive, right? Positive 7 over 3. And then we can verify that easily by plotting these points, which again we could have done in the first place, but the norm is to, when you're given coordinates like this and not the graph in advance, then this is the formula that you're told to use. That's the orthodox way. Anyway, so we plot these 2 points, and let's count up. And then rise over run. 1, 2, 3, 4, 5, 6, 7. Positive 7 rise, and then to the right 3. There we go. So that did verify that. Okay, so hey, not a whole lot of objectives here, just being able to take a line and be able to count your rise combined with your run to go from point to point to get your rise over run slope, or taking 2 points, 2 ordered pairs, and being able to plug them into this really, really, really important formula. So we're hopefully getting used to this formula. All right, the next phase of the lesson, you're going to be turning to this discovery handout. So in a few seconds, you're going to do like a hard pause on the video, or you or the substitute going to do a hard pause here in a few seconds. But all you're really doing, you're going to get some practice with counting and using the formula. But also my hope is that you discover something, or maybe rediscover something you already knew. So let's see, I don't know, you can play it by ear, the substitute can play it by ear, but I'm thinking at least 10 minutes, so 10 minutes or so, but kind of play it by ear. Once everyone is pretty much done or getting done, unpause the video and kind of we'll run through just to make sure that people were discovering what they were supposed to discover. So go ahead and do a hard pause on the video now and go ahead and do this. Alright, I'm going to carry on here as if you've unpaused. So if you still need to pause the video, do it now, because I'm about to move on with this. Alright? So here we go. Again, hopefully you've already attempted this and maybe tried to discover some things on your own here. But here we go. So what is the slope of this line? Hopefully you realized that this ended up being positive 3/2. Okay, positive 3/2. That was up 3 and then right 2. And then for number 2, hopefully you ended up getting negative 4/5 for the slope. That's down 4 and then right 5. Okay, so negative 4 over like a positive 5. Not too much to discover there. Okay, not too much to discover there. The discoveries start with these ones, 3, 4, and 5. So hope this made sense, how you were supposed to count from A to B. That was up 2, right 3. Then you were supposed to count from B to C. That was also up 2, right 3. Then, oh my gosh, then we got a little crazy, and you were supposed to count from A to C. Well, when you did that, what you should have got was up 4, right 6, which ended up also being 2/3 for your slope, of course, right? So what was the point of this? No pun intended. But what were you supposed to discover here? You know, what was the whole idea? The whole idea was this. It doesn't matter what 2 points you pick. You know, again, as long as you're picking nice integer points to start and stop counting, it doesn't matter if you picked A and C, B and C, A and B. It doesn't matter, like, because there was more than 2 points you could have picked. So it doesn't matter what 2 points you pick to count your slope. You should still get, at the end of the day, the same final answer. And then here we go with these. Number 6, number 7, number 8, number 9. For number 6, if you were counting from A to B, you were going up and then right. But if you were counting B to A, you were going to be going down and then left. Remember, down is a negative direction for rise, and then left is a negative direction for run. So this ended up being negative 2 over negative 3, but of course you still get overall a positive 2/3. Right? Because a positive 2 over a positive 3 is still positive, just like negative over negative. With 8 and 9, if you were going from A to B, you were going down and right. But if you're going from B to A, you were going up and then left. So a positive 5 over a negative 3. But again, either way, a negative over a positive or a positive over a negative, the overall slope was still going to be negative 5/3. So what was the whole point here? Well, the whole idea here, the discovery here was, doesn't matter which dot you start counting at and which dot you stop. It doesn't matter what direction you count. You're still going to get the same final answer for your slope. And then number 10 and number 11, right? Number 10 and number 11, you were supposed to run through this formula with negative 2 comma negative 3 being your x1 and y1, and then getting 2/5, right? Doing y2 minus y1. But then in number 11, you were supposed to like switch them, you know. So now 3 comma negative 1 was like your x1 and your y1. So basically you just ran through this formula twice for the same coordinates, but they were switched around for number 11. Okay, but guess what? You still should have got 2/5, positive 2/5. So obviously I don't know how obvious it was, but so the discovery here was, it doesn't matter which point you call your first x and y and which point you call your second x and y, right? Doesn't matter if this is your x1, y1 or if this is your x1, y1. Doesn't matter. You're still obviously going to get the same final answer. for your slope using this really important formula, y2 minus y1 all over x2 minus x1. All right, now I just remembered this. Let's circle all the way back to this, okay, before we end the video and move on with homework and such. So here we go. Uphill, downhill, positive slope, negative slope, but what about horizontal and vertical? Let's talk for like a minute here why the slope ends up equaling 0 and why vertical lines have no slope at all. Well, just think about it, right? At this point, I don't think you necessarily need me to explain it, but I will. If you have a horizontal line, okay, let's make this real nice, I guess. Let's go green. So let's say you have a horizontal line and you are calculating the slope of that, right? I mean, what's slope? What's the definition of slope, people? It's rise over run. Well, if you're going from like this green dot to this green dot, okay, on this horizontal line or any horizontal line, what's your rise? Oh yeah, your rise is 0, and then what's your run? Well, your run is whatever, like I don't know if this would be like 3 or 5 or 10, but I know the rise is definitely 0. So right, any horizontal line, it's going to be, for rise over run, it's going to be like 0 over whatever, it doesn't matter. So that's why overall your slope of any horizontal line is 0. Well, how about vertical lines? What's 0 here? The run is 0 here. So if you're doing rise over run, and the rise is like whatever, 7, 3, 12, doesn't matter. The run from this dot to this dot is 0. So if you were doing like 7 over 0, what is that? What's 7 divided by 0? I hope what's popping into your brain is like that doesn't exist. Like, we can't divide by 0. It's undefined. It doesn't exist. And that's basically why vertical lines have what we call no slope at all, or undefined slope. It's because when you calculate the slope of a vertical line, you are trying to divide by 0, and that is undefined. So that's why horizontal lines have slope equal to 0, but vertical lines have no slope at all, or undefined slope. All right, I think that does it for the lesson. So, time to get out your 4-1 homework and get cracking on that.